one-way ANOVA. We've been looking at the t-test, and we looked at independent t-test or the paired t-tests. These types of tests compare only two groups of samples. But if you have more samples, what will you do? Will you be comparing the two, then when you finish, you got again compare the two? It will be tedious. So if you have more than 3 groups, it's prudent for a researcher to use one-way ANOVA. ANOVA is analysis of variance. So you consider the groups that you're having, and you'll be able to consider how these groups, you consider their mean, and when you look at the mean, you will have to carry out an analysis and see how these groups differ in their variances or in their means. So one-way ANOVA brings us a way of analyzing groups of samples that are more than 2. But if you have 2 groups, you can simply use independent t-tests, or you can use pairwise or paired t-tests. So today, you'll allow me to look at one-way ANOVA. There is also some mathematics that is involved. We are going to do a lot of calculation in this one-way ANOVA, and I will require that we be attentive on what I'm going to be doing, because I'll be doing the manual calculation. Then thereafter, I will move to the SPSS generated tables, and we'll see how we are able to interpret these SPSS generated tables. Before I go on, I've sent the second assignment on our email address, and that second assignment concerns ANOVA. So allow me to move on. So one-way ANOVA compares, as I said, the mean of 2 groups you are interested in, and determine whether any of these groups are statistically significant, different from each other. Specifically, if we have the null hypothesis that there is no difference among the mean of the groups. And I have given this formula here, that if you have the null hypothesis presented by H subscript O, that the mean in the first group, and the mean in the second group, and the mean in the third group, and the mean of another group represented by UK, all these means are equal. There's no difference in the means of these groups. That is our null hypothesis, that there is no mean, there is no difference in the mean of this. And here, mu represents the group mean, and k is representing the number of groups. So this k is a number of groups that is unknown. So you can compare the mean of different groups up to the number of groups you want. And here we are saying k being the number of unknown groups. However, the one-way ANOVA returns a statistical significant result. We accept the alternative. So it's very important that what we are going to see here, if we are going to get a significant result, we will have to accept the alternative hypothesis, which says that there might be a difference in the mean of the groups that you are considering. So we are going to look at the groups, and if we go to see the significance, if the results are significant, then we reject the null hypothesis and we accept the alternative hypothesis. Very important as we move on. So the assumptions, as for all these tests that we have in statistics, the assumptions, and if one violates these assumptions, then it will be very difficult for you to give valid results. So what are some of the assumptions that are considered in Anova? One, the dependent variable is normally distributed. The dependent variable. So here we have two variables, the independent variable and the dependent variable. So the dependent variable always is normally distributed in each group that is being compared in one way or another. This means the normality of groups in one way or another, it can never tolerate the non-normal data. This means that if you have your data that is skewed or is ketonic distributed with us only a small effect on the type 1 error rate. So you are supposed to look at the skewness of your data. Look at the skewness of your data. And in our first course, or when you're doing the masters, you are told about positively skewed data and negatively skewed data. And when we look at the kurtosis of the data, we have plateau. We have the platonic data, which have something like flood pop. That is kind of a dangerous data if you are dealing with such like a data. So kurtosis data, which has, if you are drawing a data and then you have a data that moves on like that, it does not have a bell shape. But when you get to the top of the top of the data, there is flat plateau. The flat plateau with that data. This data is dangerous and you cannot use Anova. So you must have a data that is normally distributed. We were drawing the normal curve and we saw that the normal curve is bell-shaped, and we saw how much data is at the center, the distribution of this data, and how much data falls on the waysides. So this plateautosis data is having a problem. It affects how we analyze our data. And this one will leave you with two options. One of the options is to use some logarithms that will correct your data so that it can give you a non-distributed data. Or you'll have to use non-parametric, you'll have to use non-parametric statistics such as Kurzweil's H-test, which does not require the assumption of normality. So we are saying that it's very important that you make sure that your data, especially the dependent variable, is normally distributed. If not, you're going to run into trouble of analyzing this data, and some way of looking at the data and seeing that my data is not actually normally distributed is when you try to have it draw the normal distribution curve and the kind of the data that will produce the platyptosis, the one that has a plat hipped, not hipped at the top, but produces the top is we have a plateau. That one is a problematic data, and you'll have to consider either to make sure that you use various algorithms to give you to work on your data so that they give you a normal data, or choose to use non-parametric statistics, and one of them is Kurzweil's H-test, which can work without normality. Also, we talked when we are looking at the other tests of t-tests, we'll talk so much on homogeneity or variance. So in this and in this test also, you are supposed to consider and make sure that your data is homogeneous. This means that the population varies in each group are equal. There are two tests that you can run that are applicable when assumption of variance has been violated. I said you can use Schwartz, or you can now use also Brown and Forstey tests. These tests are in the SPSS. So if you run them, you'll not have any problem. For most situations, it has been shown that Wells test is the best. Alternatively, you could run Kurzweil's H-test if this assumption is violated. Another one is independency of the observation. This is mostly a study design issue. So when you are designing your study design, make sure that the design you are going to use is not prone to errors. Okay, or when you are collecting your data, it gives you enough room to collect your data so that you can be able to analyze your data without any problem. So this one is, most cases, somebody will look at your study design, which design are you using? And we'll look at what are the weaknesses of this design. Is it prone to some of the weaknesses that can give you wrong results when you use some of these tests? So you are supposed to be very careful when you are choosing on your study design. You look at the one, because there are so many, not so many, but they are accessible number. You look at them and you decide that if I use this one, then my study is not going to be affected my study is not going to be affected when I will be doing the analysis of the results. So in this analysis, the dependent variable should always be measured at interval or ratio. And when these two are combined together, interval and ratio, we call this kind of scenario as continuous variable. So your dependent variable should be on the continuous scale. So you cannot have it on a normal scale or on an ordinal scale and you say that you're going to use Anova. You'll have violated this assumption and you'll run into trouble. Another thing, your independent variable should be of two or more categorical. That means that you should have one group, second group, third group, fourth group as such. Then you'll be able to move on well. But if you are going to measure this one at a continuous interval, then it's going to bring some trouble. So make sure that your independent variable is at categorical. When groups, you are able to group in one group, second group, third group, and as such. Also, very important, there should be no significant outliers in your data, because outliers are these points that can affect your data and they can distort the pattern of your data. So you look for these significant outliers that they should not be there in the data, so that when you are getting your results and comparing the groups, the outliers are not going to affect your data. If your study design do not involve one independent variable and one independent variable, but also a third variable known as a covariate that you want to statistically control, you may need to perform ANCOVA, analysis of covariance. If there is a variable you are going to control, then you'll do ANCOVA, which is analysis of covariance. Let me not go so much in that. So I have an example here, which we are going to work out. There are teaching methods, and we want to see whether a teacher having used this method, method 1, it's independent. Method 2, independent. Method 3, independent. So that is categorical. But when you see how we are scoring these methods of teaching, like how much the student is scoring, 15, 18, 19, 22, and 11, that is in method 1. And in method 2, we have a student scoring 22, 27, 18, 21, and 17. And in method 3, a student is scoring 18, 24, 19, 46, and 22. So we want to see, these are 3 methods of teaching. If they were 2 methods, method 1 and 2, we could comfortably use t-tests, independent t-tests. But because we are having 3, now we go to ANOVA, one-way ANOVA. Now, we are going first of all now to use the manual method, which is somehow tedious, and I will pray that you follow me through. So the first thing in this process, you'll have to calculate the degree of freedom. And we are having a table here, and the degree of freedom is calculated somehow different from the other groups we deal with. In this group, we are going to calculate the degree of freedom between the groups, and the degree of freedom within the groups, and the degree of freedom in the total groups. I've said we are going to calculate the degree of freedom between the groups, within the groups, and the total groups. I'll give you some time to copy that table so that I'll be able to explain what is happening here. We finished. Let me now move back to my data. In my data, in group 1.
Hello.
Yes.
Hello, Doctor.
Yes.
We are not.
You have not finished?
No. Okay.
Okay, let me bring it back.
We are through now.
Are we through?
Yes,
Yeah.
Doctor.
Now I want to go back because I want to explain now this table using the data that we have in this. When you look, method 1 has how many samples? Method 1 has 1, 2, 3, 4, 5. Method 2 has 1, 2, 3, 4, 5. And method 3 has 1, 2, 3, 4, 5. So the total number of all the samples, that one we are calling it the population. Sample 1 in method 1, sample 2 in method 2, and sample 3. The total are 15. So N is representing the total population. Total population. N represents the total population. And in our case, the total population is 15. If you counted all from all the samples, you'll get there are 15. So our total population is 15. Now K represents the number of groups. So we have group 1, group 2, group 3. So K represents the number of groups. So in this case, we have 3 groups. And that's why we are seeing here, it is 3 minus 1, you get 2. Now, N being the number of the population, and there are 15, you get here we are having 15 minus the number of the groups, we are getting 12. And finally, we get the total population minus 1, which is 15 minus 1, we get 14. This information, we will use it later. It's very important that we keep it. We will use it later in our study. So we have said it's very important you to note that we are going to have our data between the groups, within the groups, and the total samples. So allow me to move on. Now, the second step is to calculate the mean of each group. The second step is to calculate the mean of each group. So method 1, if you take 15 plus 18 plus 19 plus 22 plus 11, and you divide by the number of the sample size, which is 5, you'll get the mean is 17. So that is our mean 1, x1. In method 2 of teaching, we have 22, 27, 18, 21, and 17. If we have to calculate the mean, which is represented by x2, the mean of this group is 21. And in method 3 of teaching, we have 18, 24, 19, 46, and 22. So the mean mark in this one, x3, is 25.8. Also give you some time to copy the table. If you are finished, you tell me I finished, or you may move on.
I have finished.
Other members? Who has not finished? Silence means that we have finished. We move on. So the most important thing here on this table, the most important thing on this table, it is the mean that we have calculated. The mean, the second mean that we have calculated, and the third mean that we have calculated. Now, we are going to look at the variance of each group. We are going to be minusing each group with its own mean. For example, we take group method 1, and then we minus the mean here. We minus the mean here, which is 17. We minus the mean there, which is 17. We minus the mean there, which is 17. And we minus the mean there. Here also, we are going to minus the mean, which is 21. Here, we are going to minus the mean also, which is 21, all through, up to the last one, 21, 21. And finally, that group, we are going to minus with its own mean, which is 25.8 minus 25.8, like that, up to the end. But before we go there, I found that the mean of group 1 is 17. The group of method 2 is 21, and the mean of group 3, method 3, is 28. Now you get all these mean, add them together, and divide by the number of the groups. So you take 17 plus 21 plus 25.8, divide by 3, because there are 3 groups. You get the grand total mean. There's what we call the grand total mean is 21.3. Also very important, we will use this mean elsewhere in our example. So this table that is following, seems that these people are having, they have cut my, I have not subscribed. They are telling me that I am remaining with 10 minutes. So what we'll do, when the time ends, we will just log out and log in again. Then we move on. So that's what they want us to do. Sasa wamepoteza nini yangu. What are they doing? Hope everyone is seeing my screen.
Yes, doctor.
Oh, it has come back.
Seeing it.
Okay, thank you. So we are moving on. Now, you see what I'm doing with the method 1? I'm taking 15 minus 17, 18 minus 17, 19 minus 17, 22 minus 17, and 11 minus 17. I'm getting negative 2 in the first one, 1 in the second, 2 in the third, 5 in the fourth, and 16. What I'm going to do now, I'm going to multiply or square this difference I'm getting. So when you square 2, you get 4. When you square 1, it's 1. When you square 2, it's 4. And when you square 5, it's 25. And when you square 6, it is 36. So you add all of them to get the summation of this group. So the summation is 70. You will do the same thing to the second group. The second group, we had 22, 27, 18, 21, 17. Then when you get the difference, you square the difference so that you'll be getting the difference is 1, you square it is 1. The difference for the second one is 6, you square it at 6. The third one is negative 3, you square it, you get 9. And you have 3 as 0, you square 0, of course, you get 0. And negative 4, you're able to get 16. And you sum all of them in that group. Then we go to the third group. Subtract, then you get the difference, then you square, the way we have squared here, and then you get the summation of the members in this group. So after you finish that, now you take the entire data, which I'm calling the population, from the first group. But before you do that, just add the mean you got in the first, the mean you got in the second, the mean you got in the third, and that one is being called the sum of the squares from the mean, which is also called the sum of the squares within. The sum of the squares of the mean, which is also called SS within, sum of the squares within. So the first average we got 70, it's there. The second one we got 62. The third one we got 502. So when we add all of them, it's called the sum of the squares within. And now we are going to calculate the sum of the squares between. And this is what you're going to do. We are going to take the entire data, the population, and we are starting from the first method, second, and then the third method. Then the mean for this, we got it was 21. The grand total mean for the population, it was 21.3. We took the mean for the first method, the mean for the second method, and the mean for the third method. We added them together and we divided by 3. So this mean is what we are having here, is what we are subtracting from every data in the group. And when you get the data from the group, you subtract and you also square. So we are calling this one sum of squares total. Sum of the squares total. So when you do what we have been doing with the rest of the data, you add all of them down there. So the sum will be 559. Then how do you get the sum of the squares between? The sum of the squares between equals to the sum of the squares total minus the sum of the squares within. Sum of the squares between equals to sum of the squares total minus sum of the squares within. And if you remember, the sum of the squares between, we took the sums of the first one plus the sum of the second one plus the sum of the third one, we got 664. Then the sum of the squares total is down here as 859. So when we subtract, we get 194 as the sum of the squares between. The sum of the squares between. Then we move to the next level. We want now to get our F critical. Now the mean squared between. The mean squared between equals to the sum squares between all over the degree of freedom between. Some mean squared between, which is MS between, equals to sum of squares between, and you remember, sum of squares between, we have just calculated it, and degree of freedom. Remember what we had at the beginning. Degree of freedom between, we got it, the groups minus 1. There were 3 groups, minus 1, we got the degree of freedom as 2. So we get this now, the degree of freedom between, now we bring it here. We bring it there. So it's 194.2 over 2. Now we're able to get 94.1. 97, not 94, 97.1. Then we move on to calculate the sum of squares within. What we have been calculating is the sum of squares between. So we move to the second level and we calculate the sum of squares within. So the sum of the squares within equals to sum of squares within. What am I saying? The mean squares between, which is MS within, equals to sum of squares within over degree of freedom within. And the sum of squares within, it's here, it was 664. And the degree of freedom between, it was n minus k, which is 12. 15 minus 3 is 12. So this one will be 664.8 over 12, which is 55.4. Now we calculate now our F statistic. Our F statistic, which is now MS between all over MS within. You see, mean square between, which was SS between over different degree of freedom between, was 97.1. And MS within, which is equal to 664.8 over 12, which is 55.4. So this one, now we calculate the F statistic, where we are coming now. The F statistic is very important in our case here. So when we calculate, it's 1.75. Now, we have now to go to, you can